fit test. So let's get into the goodness of fit tests. Did I put them under week 7? No, because those are not the annotated notes. Oh, they are. Huh, I guess I just misplaced them. Okay, yeah. So currently I put them under chapter 7, well, under week 7 versus putting them in the annotated notes. Here, let me put them in the annotated notes. So that way we should be all good. All good, all good. So segment 2. No, let's get this face out. Tour schedule. At the bottom. Yeah. All right, there you go. So those are the week. Oh, that's chapter 11 notes. So now they're under annotated notes. So they're back where they belong. All right, so today we're going to get into chapter 12. So chapter 12 is a pretty cool topic because chapter 12 kind of going back to, if you kind of remember chapter 4.4, where we're doing the contingency table and we're trying to figure out, like, do we have, like, is there association or is there not an association? That what chapter 12 is going to be doing. It's going to help us try to see if we have an association. So the first one we're going to be going over is something called the goodness of fit test. So the goodness of fit test is just testing to see how good of a model do we have. So for this one, the goodness of fit test is usually used for categorical data sets. So for the goodness of fit test, we're testing to see how well our pretty much data set that we collected fit what it actually should have been. So kind of to give you like an example, say like for all the month, you should be expecting the same amount of rain. So say on January, you should expect the same amount of rain as in December. So what the goodness of fit test is testing to see like how much rain do we get in each month. And since we're saying that all months are equally likely, our sample should be the same thing. So saying like in January, we get 5 days of rain. February, we get 6 days of rain. In March, we get 3 days of rain. What the goodness of fit is trying to see like, is everything the same? So does it follow that distribution? So if it does follow that distribution, we're going to say it's a good fit. If it doesn't follow that distribution, we're going to say it's a bad fit. So that's kind of how the goodness of fit works. So up next, we're going to go over how to find the expected value or the expected count. So K represents the number of category in the experiment. So if you kind of remember the example that I just gave you right now, K will represent how many months there are in the year. So in that example, K will represent 12 because there are 12 different months. So K will be 12 because there are 12 different category. All right, so 2, it says N has to be an independent trial of an experiment where K is greater than or equal to 3 mutually exclusive possible outcomes. So you're saying that the sample size must be all independent, and for our K, we should have more than 3, well, we should have more than or equal to 3 category. All right. So P1 represents the probability of observing the first outcome, and E1 represents the expected count of the first outcome. So P2 represents the probability of observing the second outcome, and E2 represents the expected count of the second outcome, and so on. So in order to get E1 or E2, so E1 and E2 is our expected value. So if you want to get the expected value, you do N times P1. All right. So say, for my example, say if we get 20 days of rain, or let's say we get, gotta put down, wanna use the pen. So say if we get 30 days of rain, and will equal to 30. And since we have 12 months and we're saying that all months should have the same amount of rain, you do 30 times 1 out of 12. And if you do 30 times 1 out of 12, you get 2.5. So the expected value for each month should be 2.5 rainy days. All right. Any question in regard to the expected value? All right, so let me minimize this wheel. Perfect. So let's go on down. All right, so we're gonna do this problem. So this problem you have to practice on how to find the expected value. So this is the retail market share. So here are all the publisher, well, not all of them, of different comic books. So we have publisher like Marvel Comic, DC Comic, Image Comic, IDW Publishing, Dark Horse Comics, so on and so forth. And if you look right here, just tell me how much percent of the share do they have? So say if we have a certain amount of comic book, this is how many comic book they develop all together. So pretty much Marvel has 39.98% of the comic book share. DC Comic has 29.33% of the comic book share, so on and so forth. So for this problem, it said if a comic book store sold 500 comic book in a month, how many comic books should we expect was sold from each publisher? So we're gonna say this is publisher 1, 2, 3, 4, 5, 6, 7, and 8. So for this one, what would be my K value? What would K equal to? Well, if you look at how many different category I have, K will actually just equal to, I accidentally put X. Okay, is equal to 8. So what we're gonna do, we're gonna find the expected value. So if a comic book sold 500 comic book, we're gonna see how many should each one of them expect to sell. No, I don't take up the whole screen. All right, so let's go ahead and do this next problem. So let's see how many should we expect Marvel to sell. So we're gonna find the expected for 1. So we do 500, and we multiply it by the percentage of share that Marvel has, which is 0.3998. So if I go ahead and do that on my calculator, we do 500 times 0.3998. All right, so if you do that, you get 19.99. So that's how many comic book we should expect them to sell. But if you look at that, that number is extremely wrong, because I multiplied times 50, not 500. All right. So let me get my eraser. Let's erase this. And let's put 199.9. All right. Everybody get how we got the expected value for Marvel comic books? All right. So let me do something real quick. Let me shut down all of these. shut down Spotify. Let's also shut you down. All right, good. So now let's do for DC Comic. So for DC Comic, where that's going to be E2. So we do 500 because that's how many comic book was sold for for the comic book shop. But we want to multiply that by 0.2933 because that's how many. That's the percentage of books that are sold that are published by DC Comic. So if we do 500 times 0.2933. You get 146.65. So that's for DC Comic. So now let's do image. So image will be E3. So that'll be 500 multiplied by 0.0560. If you do 500 times 0.0560, you got 28. So let's do E4. So for E4 is IDW publishing. So that's 500 times 0.0405. So 500 times 0.0405. All right, so you got 20.25. Let's do this for E5. So for E5, that's dark horse. So we do 500 times 0.0309. And you get 15.45. Then we do this for the Boom Studio. So from Boom Studio, they had 3.04. So that's 15.2. Then if we do the expected value for Viz Media, that's going to be 500 times 0.0259. So we should expect them to sell 12.95 of a comic book. And lastly, we're going to do for others, which should be 1232. So one thing you should just look at the expected value. So the expected value is telling you if I have n many objects or n many people, the expected value is telling you this is what we expect each one of those people or each one of those objects to contain. So for this one, saying if I have 500 comic books that are sold, of those 500 comic books, we should expect roughly 200 of them to be based off a Marvel comic. We should expect roughly 147 of them to be by DC Comic, so on and so forth. So pretty much, if you kind of remember when we did the average for the binomial distribution, if you do n times p, pretty much we're doing the same thing. The only thing is we're essentially calling it a little bit different, but pretty much the same thing. All right, any question on how to get the expected value? All right. So let's scroll on down. All right. So here is our goodness of fit test. So the goodness of fit test is going to have something called OI. So the OI just represents the observed count. Yeah, pretty much Marvel and DC have a monopoly over this thing. Like it's pretty hard for any other comic to go stranglehold on it. So when we have OI just means that you collect the data set, and this is what actually happened. When we say E is what we say is expected to happen. So what we're trying to see if the observed value and the expected value, are they close to each other? Because if they are close to each other, that means it's a good fit. If my observed value, my expected value are completely different, and there's a pretty good gap in between it, it's kind of telling you this is not a good fit, that our model is not doing a great job at predicting it. So that's what we're doing. We're just checking to see if the observed value is pretty close to the expected value. K represent how many different categories do you have, and represent the number of independent trial of the experiment. All right, and then lastly, we have the formula. So this is our test statistic. So that's my test statistic. So in order to find my test statistic, I have to get each O and expected value. So each observed and expected value. And what I have to do, I have to subtract them. Once you subtract them, you square the two value. Well, you square the one value, the difference of the two value, and then you divide it by the expected value. Because that's going to tell you roughly, like, for this one, the closer your chi-square value is to 0, that's kind of telling you there is no difference. But the bigger your chi-square value you get, that's telling us that we have a big difference between our two observations. All right. Everybody good for the chi-square value? And I'll show you how to use the chi-square value once we actually get into a problem. But for right now, you kind of look at it and kind of understand that where you're taking the observed value and the expected value, subtracting them, and then we're trying to see how much of a difference do we have. And for this one, in order to determine the degrees of freedom, the degree of freedom is k minus 1. So it's how many degrees of freedom do we have subtracted by 1. All right. So up next, I'm going to get into some of the assumption for goodness of fit test. So when I say assumption, if you kind of remember, like in the little format that I have, where it says test the assumption, and then I tell you, like, do the null alternate hypothesis. This is what you want to check for assumption. So for the assumption, what you want all expected frequency are greater than or equal to 1. So when you get their expected value, you do want all of them to be greater than or equal to 1. If you have something that's less than 1, then you might have an issue because you want everything to be greater than or equal to 1. Part B says no more than 20% of the expected frequency are less than 5. So if you kind of go back to what we did, if you look at all of these expected value, all of these expected value are greater than 5. So in this one, that would check out because all of my expected value are greater than or equal to 1. And if you look at it, we don't have more than 20% of our data set that's less than 5. So that's what you want to check. Just check the expected value and just make sure the expected value is greater than 1. And also, like, we really want all of them to actually be greater than 5, because greater than 5 is actually perfect. And that's kind of just testing out our sample size, because if we have a large sample size, we should have an expected value that's greater than or equal to 5. All right. So let's get to the null and the alternate hypothesis. So for this one, the nice thing about the null and alternate hypothesis is pretty much is always going to be the same for every single problem. It is never going to change. So if you look at the null hypothesis, the random variable follow a certain distribution. So when we say this, that means that my observed value and my expected value, they're pretty much close to each other, or they're identical to each other. So saying that the model that they gave us is pretty much is exactly what we actually got when we got our sample. So the null hypothesis stating that our observed value and our expected value, they're pretty much close to each other. My alternate hypothesis is stating that it does not follow the distribution in the null hypothesis. So now the alternate hypothesis is stating that my observed value and my expected value, well, we have too much of a difference between the two of them. And we should say that it doesn't follow the distribution. So the null hypothesis is it follows a certain distribution. The alternate hypothesis is it does not follow a certain distribution. All right, but everybody good for the null and alternate hypothesis? And let's see. Cool. I am recording. All right. So in order to get the chi-square value, we're going to do this with our TI-84. So for the TI-84, I put the instruction right here. Hopefully it's easy to understand. So like the first thing we're going to do, we're going to go to stats and click on edit. In L1, you're going to put all of your observed value. For L2, you input all of your expected value. Then once you input your observed value and your expected value, you go to stats, you go to test, and we're going to do a chi-square GOF test. And then you press enter. Once you press enter, what you want to do, L1 is for the observed and L2 for expected. Cool. So then you want to say enter the appropriate degrees of freedom. So you say K minus 1, that's your degrees of freedom. And then what you want to do, you want to choose calculate and press enter. So that's how we're going to do it. What are TI-84? Any question for the TI-84? Cool. So let's scroll on down. So we're going to do our very first problem. So for this one, the problem we're going to do it for M&M. So for this one, we're going to test to see if the distribution that the company or the manufacturer M&M give us, did that follow what we actually got when we actually open up a bag of M&M? Well, for this one, several bags of M&M because we had 300 M&M. So for this one, it says, according to the manufacturer of M&M candy, the color distribution for plain chocolate M&M is 13% brown, 13% red, 14% yellow, 24% blue, 20% orange, and lastly, 16% green. So this is kind of like when you get a bag of M&M, this is the distribution that they wanted to hold. So if you notice, which color do we have the most of, or should we have the most of? Oh, chatty crowd. Blue, perfect. So you should get blue. Here, let me stop my video for that way there won't be a lag or anything like that. So yeah, so blue should be the one that we should expect to have more candy of. Which candy should we expect to have the least amount of? Perfect, brown and red. All right, so let's go ahead and do some basic cleanup work. So let's find K, and also let's find N. So remember, K is how many different categories do we have? N is how many total samples do we have? So for this one, how many different colors do we have? 6, perfect. So K will equal to 6, so I have 6 different groups. All right, what about my N? How many plain M&M did we get? Yeah, 300. Great. All right, everybody go with that? Cool. Everybody's good with that. All right. So if you look at the sentence right below, it says test at a significant level of 5% that the random variable follow a certain distribution. So this is what we're testing. We're trying to test that it follow a certain distribution. So if you look right here, number 1, where it says in a sentence describe what is being tested, we'll say we are testing if the sample follow the distribution that the that the manufacturer gave us. All right. All right, so here comes the fun part. So the fun part is we're gonna be labeling the N and the P's. Let's do that. So first we're gonna label our thing. So I'm gonna say this is group 1. Oops. So let's say this is group 1. This is group 2. This is group 3, group 4, group 5, group 6. So those are my different categories. Because if you look right here for step number 2, it says label N1, label P1, label N2, label P2. All right, so, oh, you know what? That's a typo. It shouldn't have N1 because N is pretty much going to be, well, N should just be 300. I have to fix that. Nah. So for this one, what's P1? What's the probability we get a brown candy? Yeah, 13%. All right, what's the probability we get a red candy? Yeah, 0.13, perfect. What's the probability we get a yellow candy? Cool. All right, so the probability we get a blue candy is 0.24. Gotta fix that. And the probability we get a orange candy is 0.20. The probability we get a green candy is 0.16. All right, everybody good for that? Okay, so now we're gonna put O1. So O1 just represents the observed value for brown. So of the 300 candy, how many of them actually turn out to be brown? So right here, O1 is 56. How many of the red candy turn out to be, well, how many of the 300 candy turn out to be red? So 44, 47, 62, 53, and 38. All right then. Yeah, definitely more space. All right. Everybody good so far for 3? And also just know for this is a typo. It shouldn't have all of these N1, N2. All of them should be N. And you got too excited to do all of these subscripts. All right, so let's do this one. So let's find the expected value of 1. So for the expected value of 1, we get N, which is 300. And we multiply that by P1, and we said P1 was 0.13. So if I do 300 times 0.13, what would I get? 300 times 0.13. If you look at that, you get 39. Good job. So now I'm going to do E2. So E2 is expected for red. So for red, we do 300. We multiply by P2, where P2 we said was once again going to be 0.13. So the good thing about this, since we already did it for E1, E2 should be the same. So we had 39. So then we're going to get E3. So E3, we do 300. We multiply by P3. P3 we said was 0.14. If you multiply that, it should be 42. If my mental math is correct. Hopefully it is. For E4 you do 300 and you multiply by P4. So P4 will be 0.24. So you do 300 times 0.24, you get 72. And then we get E5. E5, you do 300. You multiply that by P5. P5 we said was going to be 0.20. If you do 300 times 0.20, you get 60. And then lastly, E6. E6, you do 300 and you multiply that by P6, which is 0.16. So 300 times 0.16. All right, so those are my expected value. Any question on how we got those expected value? All right, cool. So once you get the expected value, if you look at all of the expected value, I'm gonna put them right here, just for that we can kind of see if there's a big difference or they're pretty close to each other. All right, so let's look at Brown. At Brown, when we got the 300 candidate, we actually got 56 and the expected value should have been 39. So if you look at those two numbers, are they pretty close to each other or do we have like a kind of a significant difference? Yeah, they're not that close. Like you kind of want them to expect them to be a little bit close. So that's not a good start. All right, let's go to red. So for red, when we got the candy, we got 44 red candy, but actually 39, the expected value should have been 39. So for this one, are they pretty close or do we got a kind of big gap in between? Yeah, that one's better because if you look at it, it's not only 5 away from it, so it's getting better. So let's do yellow. Yellow, it was supposed, we got 47 and it was saying it was supposed to be 42. If you look at it, that's pretty close. If you look at blue, it was saying we got 62 blue, but my expected value is telling me we should have gotten 72 blue. So that's kind of telling us we're a little bit more off. If you look at orange, orange is telling us we got 53, but the expected value was 60. So once again, it's kind of roughly close to it. And lastly, for green we got observe is 38, expected value is 48. But you kind of remember this is a sample. Like our sample and our expected value is never going to be exactly the same. There's always going to be some deviation from them. But what we were trying to do with this pretty much study is see if the deviation is so small that we could say that D2 follow the distribution, or is the deviation too big that we have to say it doesn't follow the distribution? All right, so that's what we're trying to find out. We're trying to see, does this distribution follow the model? Okay, so for this one, what we want to do, we want to check for assumption. So I recommend checking this assumption first. Let's check if all the expected value are greater than 5. So if I look at all my expected value, are they greater than 5? Yes. So if all of my expected value are greater than 5, we don't really need to check this one to check to see if all expected value are greater than 1, because this will also check out. So you always start with the bigger one, because if all of them are greater than 5, then essentially you can go ahead and go on to the next problem. Like the only time you have to stop and really check on it, if all of them are not greater than 5, you at least want 80% of them to be greater than 5. So if 80% are greater than 5, so say if we get 5 expected value greater than 5, but we get 1 expected value that's less than 5, that's okay, because more than 80% of the expected value are greater than 5. All right, but any question for the no, for the check the assumption? All right, so let's do step 5. So for step 5, what we want to do, we want to do the null alternative hypothesis. So let me actually type this out. So for the null hypothesis, it will be follow the distribution. Let me see if I can fit that in. Almost. And for the alternative hypothesis will be does not follow the distribution. So that's my null hypothesis. So the null hypothesis will be it follow the distribution. The alternative hypothesis will be that it does not follow the distribution. Everybody good with that so far? All right, so up next we're gonna go ahead and do the goodness of fit test. So we're gonna do this with the calculator. So let's do the TI-84. So for the TI-84, remember, we're gonna put this in L1. We're gonna put this in L2. Oh, let me move this over here. All right, so first we're gonna go to stats. We're gonna go to edit. I'm gonna clear this list. And I'm gonna clear this list over here. So in L1, I'm gonna enter all of the observed values. So I'm gonna do 56, 44, 47, 62, 53, 38. Out. All right, so that's my observed value. For my expected value, we're gonna put 39, 39, 42. And when you're entering this, it's very important that you put them in the order that they are. So say like for 56, for the brown, it should correspond to 39 with the expected value. So it should be in the same row. So if you put 56 in the first row, 39 should also be in the first row, because if you don't, it will give you an incorrect answer. Because the way the calculator gonna look at it, it's gonna correspond the first number with the first number in L2, because you're gonna know you do L1 minus L2 and then divided by L2. All right, everybody good in regard to this? All right, so up next you're gonna go to stats, you're gonna go to tests, and in the bottom, right here, you should see something that says GOF test. You just click the GOF test. So if you look right here, it says L1. So L1 is your observed value. L2 is my expected value. So I say L1 is observed, L2 is expected. Everybody good? L1 is observed, L2 is expected. All right, lastly, what you want to do, you want to put degrees of freedom. So in this case, degrees of freedom is equal to K minus 1. My K would equal to 6. So if you do 6 minus 1, you get 5. And then you press calculate, and we're done. So if you look at the chi-square value, we get 12.9, what do you say, 94. Any question how we get chi-square of 12.94? So right here, we'll put 12.94. So the degrees of freedom, you get it by doing K minus 1. K minus 1. So you do 6 minus 1. So you get 5. All right. So also, if you look at it, you get a p-value. So the good thing about the chi-square distribution, will always be a right-tailed test. So it's not going to be a left-tailed test or a two-tailed test. It's always going to be a right-tailed test. So if you look at the p-value, it gave me a 0.03. Well, we'll say 0.024. So we'll say 0.024. So for p-value, we get 0.024. And then for alpha, let's see if I gave you one. Well, if you look right here, I said alpha was 5%. So you put 5% there. So you get p-value is equal to 0.025. You get alpha, which is equal to 0.05. Any question in regard to how you get p-value or alpha? Sweet. All right, so this should be something familiar. Which one's bigger, p-value or alpha? Cool. Alpha. So if alpha is bigger, we reject the null hypothesis. So if you look at it, I'm rejecting the fact that I follow the distribution. So if I'm saying, if we're saying that we're rejecting the null hypothesis, we're saying it does not follow the distribution. So that percentage that M&M, the manufacturer, gave us, we're saying this is not correct because based off of our sample and based off our expected value, we're saying there's too much of a difference between the two of them. So we're saying the two of them are not pretty much correlating. So we're saying that it does not follow the distribution. So for this one, let's do our conclusion. So let me type it out. So for this one, we'll say there is not enough, oh, sorry. There is enough evidence to say that the distribution does not follow the distribution that where's the N. All right, let's right click it for AI perspective. Cool. Cool. So for this one, we'll say there's not enough evidence to say that the distribution does not follow the distribution, or sorry. There is enough evidence to say that the distribution does not follow the distribution that M&M manufacturer gave us. So we're saying that the percentage that the manufacturer gave us, that how much percentage is given for each one, we're saying that that's not the same as what we actually got based off of our sample. So we're saying the two distributions are not the same. All right, and that's it for that first one. Any question for that first one? All right, let's do the second one. So for this second one, it says a casino official wants to determine whether or not a die is fair. The die was thrown 120 times with the following result using a 5% level of significance. Test that the die is fair. So pretty much what we want to do, we want to test the die is fair. So test that the die is fair. So if the die is fair, like how would I know if the die is fair? Well, if you kind of think about it, if you have a die, the die has six sides. So that means every number should happen 1 out of 6 times. So test that the die is fair by seeing if each outcome occur 1 out of 6. So that's what we're testing. We're trying to test to see if this follows the distribution of a normal die. Because if this follows the distribution of a normal die, that means every single case, pretty much all of these frequencies should be pretty close to each other. All right, so once again, let's go ahead and do P1, P2, P3, P4, P5, and P6. All right, so if you look at all of these should be 1 out of 6. Because for this one, we're kind of just using logic. You're saying, hey, since a die has 6 sides, and since each die, well, each side should be equally likely to occur, so the probability that will land on that die should be 1 out of 6. So if you look at 01, 02, 03, 04, we just want to put the observed value. So we'll say 01, which is 32, 12, 13, 21, 14, and 28. All right. So before we move on, what's my K for this problem? How many different categories do I have? 6, perfect. What's my N in this case scenario? Sweet. Like you're reading my mind. Perfect. So we get N is equal to 120, we get K is equal to 6. All right, I wasn't asking for degrees of freedom, but you gave it to me, so I'll take it. And also degrees of freedom should be equal to 5 because if you do 6 minus 1, you get 5. All right, so let's do the expected value. So just remember for this one, you multiply by N. I just made a typo and put all of these subscript, but it should be N, not the subscript. So my apologies. All right, so if we want to get the expected value for N1, well, sorry, for E1, that'll be 120, and we multiply by P1, which is 1 out of 6. So if I do 120 times 1 out of 6, what would I get? Cool, 20. So the good thing about this, each one of them should be 20. Because each one of them will be 120 times 1 out of 6, 120 times 1 out of 6. So it'll be 20, 20, 20, 20, and 20. Cool. So that's my expected value. Any question for my expected value? All right, so we're gonna check the assumption. So remember, you check the harder of the two assumption because if the harder of the two assumption pass, that means the other one is also gonna pass. So for this one, we have to check to see if all expected value are greater than or equal to 5. So if I look at all of these expected value, are all of them greater than 5? Cool. So if this one passed, that means this one will also pass. Because if all of them are greater than 5, then all of them are also greater than 1. All right, so let's do the null and let's do the alternate hypothesis. So for this one, I'm going to kind of change it up a little bit. I'm not going to put the null hypothesis follow the distribution. The alternate hypothesis is it does not follow the distribution. I'm going to put like what we're trying to do, because what we're trying to do, we're trying to see if this coin is fair. But in a test or in a quiz, if you just want to put yes, it follows the distribution or doesn't follow the distribution, you'll get full credit for that. So for the null hypothesis, if it does follow the distribution, does that mean it's a fair coin? Or not a coin, sorry, a fair die? Or does that mean that the die is not fair? If it does follow the distribution. Cool. So is a fair die. So that means the alternate hypothesis will be the die is not fair. Perfect. Good job. So yeah, so instead of putting that follow the distribution or doesn't follow the distribution, like it just makes more sense to put it this way. Gonna make it easier to do. All right, but everybody good so far, all the way through step 5? All right, so up next, what I'm gonna go ahead and do, I'm gonna go to my TI-84 and I'm gonna enter this. So remember, this goes in L, oops, gotta change it. This goes to L1 my expected value go to L2. So let me go to TI-84, which is that little rabbit over there, and let's enter it. All right, so let me clear this. All right, so for L1, we put 32, 12, 13, 21, 14, and 28. And then for L2, we put the expected value. Luckily for us, the expected value is all 20 for all of these, because pretty much it is equally likely. All of them should be the same. All right, so I have L1, I have L2. So now what I could do, I could go to stats. I could go to test. I'm gonna push the up button because the goodness fit test is all the way in the bottom. So we'll do chi-square GOF test. L1 is my observed value, L2 is my expected. My degrees of freedom is still 5 because category is equal to 6. 6 minus 1 will give me 5. So then we go to calculate. All right. So if you look at my chi-square value, we get 12.9. Ah, I guess I forgot to put chi-square value. Gotta read. So we'll do step 5 right here. So if you look at chi-square value, so we'll say chi-square is equal to 17.9. If you look at my p-value, p-value is 0.003. So I put 0.003. 0.003. So I'm going to go to, did everybody get the 17.9? Or is that wrong? Okay, cool. I saw the question mark, so I started freaking out. All right, sweet. All right, so if you look at the significant level is 5%. So right here, we have to put 0.05. All right, so if you look at my p-value is 0.003, if you look at alpha, it's 0.05. So which of the two is bigger, p-value or alpha? Alpha. So since alpha is bigger, that means we reject the null hypothesis. So we're going to reject the fact that this is a fair die. So we're going to conclude the die is not fair. So let's write that in our interpretation. So we'll say there is enough evidence to say that the die is not fair. And that's it. So say there's enough evidence to say that the die is fair. But also, you kind of should have already had like an inclination of it. Because if we compare our expected value to what we actually got, you should have seen that like our expected value and our observed value, they're pretty far off. Because if you look at like say one occurred 32 times, but the expected value should have been 20. If you look at two occurred 12 times, and we should have saw 20. If you look at 3, once again, we saw 13.3, but we should have saw 20. Like the only one that actually came close to it was 4, but every other category was pretty far off. So just by kind of eyeballing it, you should have kind of seen like, okay, something is not right with this die, because if this die is a fair die, all of them should be the same number or pretty close to the same number. All right, but that's it for that last problem. Any question for this problem? Right, so I'm definitely fixing 12. All right. So what I want you to do, I want you to practice on this next problem. So take a minute and try doing this one. Let's see. Oops. And also, if you want to check your answer, you could just private message me, or you could just put it in the chat, and that way I'll let you know if you got it right, or if you need a little bit more of an adjustment. So many typos in this. All right, so let me go over this question. So for the people who did participate and chat with me, most of y'all were able to get it correct, or we figure out how to get it correct. So good job. So let's go ahead and do this. So it said Acme Toy Company print baseball cards. The company claimed that 30% of the cards are rookie, 60% veterans, and 10% are all-star. The cards are sold in packages of 100. Suppose a random sample, a randomly selected package of card has 50 rookie, 45 veteran, and 5 all-star. So what we're trying to do, we're trying to see if it follows this distribution. So we're trying to see if the card claim is correct, because pretty much we want them to be like, it doesn't have to be exactly, say 30% of the card are rookie, but it should be pretty close to 30%. So in a sentence, describe what's being tested. We are testing the claim that the cards follow a certain distribution. All right, so just remember for N1, N2, there's no such thing as N1, N2. It is essentially 1N. So for N is equal to 100. K is equal to how many categories do we have? So the category are rookie, veteran, and all-star. So that means K is equal to 3. So that means degrees of freedom is equal to 2. Any question in regard to N is 100, K is 3, or degrees of freedom of 2. All right, no question. So the nice thing about this, well, pretty much since N is 100, it should make the expected value easier to guess. So for 30% cards are rookie, so I'm gonna say that's P1. So P1 is 0.30, P2 is veteran, so that's 0.60. And lastly, 10% are all-star, so let's say 0.10. Next thing we're gonna do, we're gonna find the expected value. So the expected value, like I said, since it's out of 100, it should be very easy to do. So if I do 100 times 0.30, you should get 30. If you do 100 times 0.60, you should get 60. If you do 100 times 0.10, you should get 10. So my expected value are 30, 60, and 100. Any question I got 30, 60, or 100? All right, so now I'm gonna go to my TI-84. So the TI-84, we're gonna go to stats, we're gonna go to edit. I'm gonna clear this list. I'm gonna clear this other list over here. So for L1, we're gonna say how many card was the observed. So for the observed was 50. So it's 50 rookie, 45 veteran, and 5 all-star. For my expected value was we should expect 30 rookies, we should expect 60 veterans, and we should expect 10 all-star. So if you look at this, there's kind of a difference because we got 50 rookie, but we should have only gotten 30 rookie. And then if you look at it, we got 45 veteran, but we should have gotten 60 veteran. So most likely for this one, we're gonna get something that says that it doesn't follow the distribution, but let's go ahead and do the chi-square test. Or sorry, chi-square GOS test. So L1 is observed, L2 is expected. For this one, we do have to change the degrees of freedom from 5 to 2, because if you do 3 minus 1, you get 2. We go ahead, calculate. All right, so if you look at chi-square, it's 19.58. So 19.58. And if you look at the p-value, well, the p-value is extremely small. Okay, if you look at some of you were having a little bit of trouble, you told me the p-value was 5.5, but immediately that should sound kind of wrong because the p-value should never be bigger than 1. But if you look right here where it says e to the -5, that's telling you move that decimal place over 5 places. So for the p-value, you should get 0.00006. And the reason why I put 6, because if you actually do look at the p-value, is 5.5. This 5 will round up this other 5 to a 6. So that's why I'm putting 6. All right, so I forgot to do a bunch of stuff. So the assumption, expected value should be greater than or equal to 5. It passes because if you look at all of these are greater than 5. So for the null hypothesis, we say follow, and we'll put doesn't follow. All right. So if you look at the alpha they gave us 5%. So we say 0.05. And we say p-value, well, p-value was extremely low, 0.0006. So if you look at my alpha, if you look at my p-value, well, we have enough evidence to reject. So if I have enough evidence to reject, we'll say there is enough evidence to support the claim that the distribution does not follow the, what was it, 60% should, 30% should be rookies. I think 60% should be veterans. Yeah. 60% should be veterans and 10% should be all-stars. So we're saying it doesn't follow this exact model. So we're saying like it doesn't give us something close to 30% rookie, it doesn't give us 60% veteran, and doesn't give us 10% all-star. So we're saying it doesn't follow this model. It follows some other model. But that's it for this one. Any question for the last problem? All right. So for this one, we're gonna do something a little bit different because for this one, I'm not gonna test you on the hypothesis test. I'm just gonna test you to see if you know how to find the expected value. So for this one, all we're gonna do, we're gonna focus on how to get the expected value, and then that's gonna be it for section 12.2. So we're only gonna focus on how to get the expected value, but in regard to you finding the hypothesis test and you testing it, I don't want you to do that. All I want you to do is know how to get the expected value for the test. So that's what we're gonna do for this one. Everybody clear on what I expect for 12.2? All right, so let's go to the one question about how to find the expected value. And then that'll be it for today. All right, so for this one, we're doing a test for independence. So usually for a test on independent, in order for us to find the expected value, what we have to do, we have to find the expected value for every single one of these. So this one is a little bit more difficult. So we have to find the expected value for each one of them. So you kind of know, these are your rows. These are your columns. So you need to make this a little bit easier. We're gonna label our column. So I'm gonna say this is column 1. This is column 2. This is column 3. And I didn't write 2 over here. So this is row 1. This is row 2. Everybody good so far with the labeling? Okay. So say if I say, I want to find the expected value of row 1, and I want to find it for column 1. This is how I will write it. I'll write it E11. So E11 means we find row 1 and then column 1. So I want to find this expected value. So I want to find what the expected value for a man and for money. So in order to find that expected value, what I have to do, I have to look at the total of that row. So how many total people do we have that are men? Let me put up the chat again. Cool, 883, perfect. Great job. So we put 883 right here. So that's how many total people do we have in row 1. So then if you look right here, it says C1 or CJ. So C stands for column. So that means we want column 1. So how many people do we have in column 1? Yeah, 128. All right, and lastly, what we want to find N. N is how many total people do we have in this study? So how many total people do we have in this study? There you go. So 1,776. So I'm gonna go ahead and do that. So let me bring out my TI-84. So you go 883 times 128 divided by 1776. And that's your expected value. So you get 63. 0.64. All right. So we have a question, why E11? So E11 is just a kind of shortcut way of how to say row 1, column 1. Because what this represent? It represent row 1. What this other one represent? It represent column 1. So you just know the first number represent which row are we looking for. The second number represents the column that we're looking for. Does that kind of make sense? It's like a shorthand way of doing that notation. Yeah. So now let's say we're gonna do, let's get a different color. Let's do red. So now let's say I want to find this one. So I want to find the expected value for that one. So for that one, which row is it in? Row 1. So we put 1 right here. Which column is it in? 2. So this will be E12. But pretty much you should know it represents, we're finding the expected value for the first row and for the second column. All right, so if you look at it, we're going to still use 883. So I'll say 883, because that's the total for row 1. But now if you look for column, we're not using column 1, we're using column 2. So what's the total for column 2? 1020. Perfect. And then you divide this by your n, which is still 1776. So let me go ahead and do the calculator on this. So for this one, if I wanted to, I actually can't do that. So we'll do 883 multiplied by 1020. And you just divide that by 1776. And if you press enter, that's our expected value. So we get 507 point, what was that point? 0.13. Right. Everybody good for that second example? All right, so let's do the third example. So the third example is going to be for this one over here. So if you look at that one's still going to be E1, but it's in column 3, so we put 1, 3. So since it's still in row 1, we still got to use 883. But which column is it in? So what should I put for the total of the column? Yeah, 628, perfect. And then you divide this by the total again. So if I do 883 times 628 and you divide that by 1776, we get 312.23. Correct. So for this one, this is for men who pick money. So men and money. This one is men and health. And for the last one is pretty much men who chose love. Yeah, well, the second row is about to happen. All right. But everybody good on these 3 expected values that we just got? Perfect. All right, so let's do now, because we already found the expected value for all 3 of the top. So now what's left is we're gonna find the expected value for the bottom now. So now we're gonna do this for the women. So for the women, which row are they in? They're in the second row. So right here you put 2, because they're in the second row. And let's do women and money. So we'll do 2, 1. So that means we're looking at row 2, sorry, and column 1. So if you look at row 2 is 893. There you go, 893. But now since we're looking at column 1, it's 128. And you divide this by 1776. Any question how I got 893 times 128 divided by 1776? Okay. So I'm gonna trust you could do that in your calculator. So I'm gonna just do that in mine right here. So I could do it a little bit faster right here. So you get 64.36. All right, so that's the expected value for the second row, column 1. So for the second row, column 1, we're expecting it should be 64.38. Any question for that first expected value? All right, so now what we're gonna do women and health. So women and health, that means we're gonna be doing expected value of row 2, column 2. So row 2 should be 893. But if you look at column 2, that should be 1020. And we divide that by 1776. Everybody got how I got 893 times 1020 divided by 1776? Right, so let's go ahead and do this. So 893 times 1020 divided by 1776. And I get 512.87. And that's it for that last expected value. So what I want you to do, I want you to practice, and I want you to do this very last one. That's weird. So I want you to find the expected value for row 2, column 3. So pretty much women and who chose love. So take a minute and try doing that one. And if you want me to double check your answer, you just put it in the chat, and I'll let you know if you got it correct. Cool. Yeah. Great job. You got it. All right, so let's do this problem. Most of you who participated, well, already gave me the answer, so no one. There you go. 893 multiplied by 628, and you divide it by 1776, and that should give you 315.77. All right. So pretty much for the final, that's like the only thing I'm going to test you for that. So just practice on how to get these numbers, and also practice when the total are not given to you. What I mean by the total, like the row total or the column total. Because for the final, I'm not going to give you that. So just know how to get the row total. So like say, if you don't have 883, you should be able to figure out how to get it. Like just add these three and you'll get the 883. But for the test, this is the only thing I'm going to ask you for 12.2. So for 12.2, you don't really have to do the homework for 12.2 because the homework is going to ask you to do like hypothesis test. So just practice on how to get the what you call it, how to get the expected value. If you know how to do the expected value for this one, you should be fine. Like for 12.1, you should focus on 12.1 because I am going to give you a problem that follow. Let's do the first one that follow this model. So do practice on these. And like if I were you, you practice on these three problems. If you're able to do these three problems, like for the test or well for the final, you should be able to do pretty good for the final. All right, but we're gonna just stop right there because since nothing past this is gonna be on the test, I don't really want to give you more than what's gonna be there. So we just stop right here. All right, but everybody, any question in regard to chapter 12? Let's stop. All right, cool. We got some questions. Or doing 12.2. No, you don't have to do the 12.2 homework. Just practice on how to get the expected value. So if you want, just go to these. Well, I already did this for the men. Yeah. If I were you, like use like these example just to practice on how to get the expected value. If you're talking about 12.1, yes. For 12.1, the null alternative hypothesis should always be the same. So if I were you for 12.1, just have the null alternative hypothesis ready because it's pretty much always going to be the same. So you already know, because I'm telling you right now, you're going to have a problem like that for the final. So yeah, have that handy for yourself. All right, sweet. Any other questions? Yeah, so you're doing chapter 10, chapter 11, and pretty much chapter 12.1 for your homework. So that's going to be the only thing due on Thursday. So yeah, so you want to make sure you have chapter 10, chapter 11, and chapter 12.1 done. For that way you can turn it in on Thursday by the end of the day. Yeah. All right. Any other questions? All right, so if you remember, I already posted the study guide for the final. So do go over that and do go over the topic and see like, okay, which of these topics do you need more help with or which topic do you not need help with? So that way for tomorrow, because remember for tomorrow, it's essentially just you asking questions. So I'm not gonna go over anything new. Yes, so for the observed value or the observed count should always be in L1. The expected value should be in L2. Yeah, so tomorrow I'm not gonna go over anything new. So any question you have or any problem you want me to go over, I'll go over that tomorrow. So for tomorrow, you pretty much have your question ready for that way. If you do have questions, you can ask me and that way I'll help you how to do it. All right, but that's it for today. Hopefully you take today quiz. Today quiz was supposed to be easy, relaxing quiz. Hopefully some of you didn't get too stressed out for the quiz, but it should have been a quick quiz. Well, the question will be similar as the test. Like some of them will, some of them won't, but it kind of depends. Like I'm not gonna tell you all the questions are gonna be the same as like previous question. There will be some new question and there will be some question I'm repeating. No, it was a good thing. All right. Any other question before I shut down this meeting? Well, remember the extra credit. The extra credit is essentially the what we call it, the test correction, because those are extra credit points that you're getting to boost up your grade. So that's the extra credit that you're getting. All right, guys. So that's it for today. So let me close out this meeting, and I'll upload the notes, and I'll upload this lecture to whenever it finishes rendering.